start the recording even though I'm barely ready. All right, you guys, come into the room. Feel your feet, please. What do your feet feel like? It's gonna be some half-assed meditation, but feel your feet. Are you just aware? I mean, can you feel them? Can you feel your big toe on your right foot? Can you feel your big toe on your left foot? Can you feel the back of your head? Can you feel your back? If you cut your body into halves, a top half and a bottom half, where do you live? What half is perceiving the world? Bottom half is cut it at the waist. Okay. Now cross your shoulders. Is your head, is your self, the thing that's perceiving the world, above your shoulders or below your shoulders? Where does it feel like you're coming from? And wherever you've chosen that, we're kind of doing some spiritual calculus here. Divide your body into thirds, a middle third and an outer 2/3. So far you've kind of narrowed it down horizontally. If we cut the other way, where do you live in that third? Where does it feel like you are? And now slicing front of the face and the back of the head, so you've got the front of your body and the back of your body. Where does it feel like you are with that cut now made? So we're cutting, trying to locate where the sense of ourself comes from. All right, now just listen to the sound of the air coming into the room. Let that fall on your eardrums. All right, let's do some calculus. Cool. Little introspection there. Feeling pretty good. Real analysis people. That stuff you guys gave me has still got me pepped up, whatever it was. What was it? How did you pronounce it? Meth? What? No. Yeah. No. I took a new supplement. I got a new supplement that is just like, I don't know, I'm feeling so good. I'm feeling like not tired for the first time in like months. It's incredible. I was joking that it was methamphetamines. Yeah, not meth. What is it? NMNH is the stuff I'm taking. NMNH. It's the precursor to this thing you lose as you get older. NAD plus, some sort of enzyme that old people have a deficiency of.
Are they pills?
They are pills. So who knows? Maybe they weren't meth pills, and they just sell them under this name, and you feel good. I remember taking some vitamins once, and everybody was like, "These vitamins are incredible. I got so much." Well, they had caffeine in them. Yeah, that'll do it. A little vitamin B, a little caffeine. Let me grab my notes. I kind of want to just practice some things today. But I am feeling really good. That's nice. You're all still fresh and your bodies haven't started rotting away, so that's good. I hope not. It's a little early. Shouldn't start till your late 40s. All right, so that's something to look forward to. Do you remember the coordinate systems we talked about last week? What were they?
Spherical.
Spherical and cylindrical. Let's just do a quick review of those. I want to think about these and only this stuff today. Because we kind of introduced it and then I wasn't super happy with the way I introduced it, so I want to practice some more with it today, because this stuff's actually pretty hard. And as a fine person in this class once said to me, Calc 3 is hard. Calc 3 is pretty hard, especially the visualizing stuff. So let's remind ourselves about cylindrical, and then we've got rectangle, right? That's kind of where we normally live. That's where we feel good. We got good old X, Y, Z there. And then cylindrical. What are my coordinates in cylindrical? What are the three coordinates I have?
R, theta, Z.
Beautiful. R, theta, Z. And let's actually draw little pictures. So X, Y, Z. So X is how far I go on the X-axis. Y is how far I go on the Y-axis. Pick that point, and then I go up Z units. So Z is the height, X is this way, Y is that way. We know how to do this. R, theta, Z, cylindrical. Well, I'm going to draw, you always kind of draw the normal rectangular coordinates so you can get your bearings, but they don't really play a role in here. So we have R, which measures, I guess I'll put X here. R measures the radius, the radial distance from the Z-axis. So this is distance from the Z-axis. That's how far out we're originating, so we pick an R direction. Theta is how far I've swept from the positive X-axis. So this is degrees or angle from positive X-axis. And then Z is just how straight up I go. So Z is the same. These Z's are the same in cylindrical and in rectangular. Same Z. Z is the height. This is just polar coordinates with a Z coordinate tacked on, and this is just a plane with a Z tacked on. And then how about spherical? What did I have there?
R, theta, and another angle variable I forget the name of.
Yeah, yes, exactly. So, but we call them rho, right? Rho, just the same thing. It's Greek R, right? We got a Greek R here. And then we had theta, and then we have this other angle phi. And this gets about as far from this as we can get. We're not really, we don't share any coordinates like we do here, where they share the Z coordinate. But there is a little bit of similarity here. It's this theta primarily. So let's get our axes up again. This is the positive X-axis. And so theta is the number, the degree sweep or radian sweep from the positive X-axis. And so right now, if I just left theta defined, I would have this plane that runs through this space. If I looked at all the points and satisfied, say, theta equals pi over 4, that would be everything that makes it a 45-degree angle with the X-axis. What would that look like if I left everything else free here? What if this is the only thing I specify? What does it look like?
Like a lot of plane, yeah.
Just a plane angled through that central axis there at theta degrees or theta radians, whatever we have there. But then we've got these other coordinates. We've got rho, which is the distance from the origin. So it's a little different than this R. This R is measured directly orthogonal to the z-axis. This rho is a little bit different. But before I can even draw it, I have to think about how far down from the positive z-axis I've fallen. So that's phi right there. And so you sweep down a certain amount from the vertical axis in this plane, whatever this plane is that we have for theta. And then you move out row units in that distance. So sweep, figure out what plane you're in. From the z-axis, come down phi, move out rho in that direction. And let's get, this part I don't expect you to remember too much, but let's do the conversion stuff. So conversion, here I'm gonna put rectangular to cylindrical. And the way this worked was, if I know the x, y, z and I want to move to cylindrical, the r is going to be the square root of x squared plus y squared, just like regular polar. You could say this. And that's actually a pretty helpful thing to keep in mind. We're gonna need practice with this today, so if you don't have this all kind of conglomerated somewhere nice to look at, definitely take some notes right now. And then theta is equal to the arctan of y over x, and z is z. That's cool. That one was easy. So this is, you're given x, y, z, and you move to this. Let's do cylindrical to rectangular. Oh my God. Oh, to rectangular. So here, over here, I was given x, y, z. I need to come up with the r theta z. Here I'm given r theta z, and I gotta come up with the x, y, z point that corresponds to it. What's x gonna be? Maybe you can help me with that. I think you can help me with this. How about low-hanging fruit? What's z?
Z.
Yeah, all right, we got it. Partial credit, 30%, 33%. What are these guys gonna be?
R cosine theta and R sine theta.
That's quite beautiful. They're just like polar coordinates. And then we've got this z tacked on. So this is the planar location, and then this is the height. This is the plane that you're in, your version of the polar coordinates. Let's do spherical. So let's do rectangular to spherical. Now let's do spherical to rectangular. This one's a little trickier to remember, and I'll show you what I kind of do to remember it. So here I'm going to be given rho, theta, phi. And the way I remember this is, first off, rho, let's see, wait, we want x, y, z, right? This one's, I'll just put them up here and then talk about them. So z is going to be rho sine of phi. X and y, these are going to have a rho, and then it's actually kind of this thing right here from the polar coordinates with a cosine of phi tacked on. So the x starts out just like this, and r is rho, cosine of theta, cosine of phi, and then I have rho sine of theta, cosine of phi, and then the sine of phi shows up here. So that's kind of a nice way to remember it. And then one more, we've got rectangular to spherical. And let's see, what do we got here? So now we've got x, y, z, and we want to get the other direction. This actually might, I know the easy low-hanging fruit is rho is square root of x squared plus y squared plus z squared. You probably want to crank that out. And let's see, the theta is the same as the theta in polar coordinates. So that's going to be arctan of y over x. Doesn't really involve the z because it's just a sweep like this. And then the phi is going to be, what the hell is the phi? Let's see. Let's just see if we can derive it here. So we've got this, and we've come down, we're out row units in that direction. We've swept down phi. So we should be able to just figure out what that angle is based upon this distance here whatever that R distance is, and then just use some trig here. So let's see, how could we find that distance right there? Well, that's gonna be square root of x squared plus y squared. So this is square root of x squared plus y squared, just that distance. And then, so I guess this is going to be, find rho up there, and then come down here, and this is going to be the arc, let's see, what is that, sine? So inverse sine of rho, this over rho. So square root of x squared plus y squared over rho. And again, this doesn't look like it's doing anything because we already can, you have to know rho before you can do that. So if you want, you could just do that. Okay, so those are our formulas. Let's get busy. Yes, sir.
Would, from the rectangular to the cylindrical, would it be x squared plus y squared?
Yeah, sorry, I forgot my squared. Thank you. Good call. Yeah, any other errors or corrections? Thanks, Talon. That's a good catch. Hopefully I wrote that elsewhere. Okay. All right, so let's play some games, some conversion games. Oh, also, last little thing, let's get the elements for volume up here. So volume element in rectangular, it's just dx, dy, dz in any combination you want. In cylindrical, it's going to be r, dr, d theta, dz. These can be in any order you want, any order. And then in spherical, it's going to be rho squared sine of phi, d rho, d theta, d phi. Again, any order on those. We did drive it. I drive that one, didn't really drive much else. So I'm gonna give you an integral, and I'd like you to just kind of, we didn't do much practice with this, but I wanna see where you're at. And I want you to see where you're at. Ooh, actually, before we even get to the integrals, here's a warm-up. Because the spherical coordinates are certainly the hardest. So could you do me a favor, sketch or identify the following? These are going to be spherical coordinates. And I want you to, what is the set of points that satisfies each of these? So here's the first one, theta equals pi. Then the next one is phi equals pi over 6. And then rho equals 2. So those are 3 separate graphs. What are the surfaces that those are describing? This is a good warm-up. Anybody want some tea? You may pour some of this in your monster drink there, Eric.
Sure, why not?
Yeah, cool. It looks mostly done. There you go. I'm gonna gladly give you more if that's not too polluted and you'd like more. It all is. I'm soon gonna be paying 10 times more for it. Yes, ma'am. Oh, this guy does the Z here.
So the top doesn't need to.
Yeah, so this has the Z in it, Camilla. Because when we come up here, this will encode kind of that Z information right there. You see what I'm saying? Because I'll know this, which is only X, Y stuff, but this hides the Z secretly. It's a good question. Anybody else have tea? Let me pour some tea on that ice. No, it doesn't sound like you're very good. Okay.
The only nice tea you can have is chai. Depending on who you ask.
This would
If you
actually
ask
blend
Kristen,
with
that's
chai.
actually not true, but.
I think there's a lot of iced tea that's not chai.
Yeah, I don't know. I don't love iced tea.
Really?
No. I like it all in a bumper for sure, like that's
Yeah.
an exception. For sure, but I don't really choose to drink iced tea. I'm gonna drink tea, it's hot. Respectfully.
No, you could, I don't have anything invested in it, it's all good. I won't be like waking up at 2 AM stewing about your dislike of iced tea.
Well, I don't dislike it, it's just not a preferable way to.
Yeah,
drink
yeah,
tea.
fair enough. To each their own. And I think it's really important that we get these down before we do the other stuff. So yeah, notice in each one of these, there's two variables that aren't mentioned. That's because they can take on all values. Kind of like looking at geodesics in a sense here. What are the fundamental curves? Define the geometry of space. Okay, how about that first one? What's that guy? Plane
Along the x-axis.
along the, pi over 6 away from the x-axis, so 30 degrees off of x. So it's kind of like this. You can kind of sketch something like this. And I'll label the counter part of it. That's going to be pi over 3 right there, because that's the complement. Pi over 3 plus pi over 6 gets you 90. And that little,
Is it pi over 6 or pi?
I'm doing pi over 6, but the difference here, from the y-axis, it would be pi over 3. It's pi over 6 from the x-axis, but pi over 6 plus pi over 3. It was just hard to draw the actual angle, so I drew the complement kind of out here. That gets me the 90. So it's definitely just that, with a little pi over 6 in that nook. But if you thought about what this angle might be, it would be pi over 3. Does that, you see what I'm saying? You want me to explain that a little more?
Yeah, how does that equal pi?
Oh, I'm looking at the wrong one. That's, I wrote the damn problem wrong, so thank you. It doesn't. But if theta was pi over 6, it would look like that. But since theta is pi, it doesn't look at all like that. What's another name for this plane right here? What happens if you sweep a full pi?
Just the XZ plane.
It's just the XZ plane. Does that sound better, Evan?
Yeah.
Okay, cool. Thanks for helping me out there. It's the XZ plane. Sweep to here. Here's your angle, and then we're looking at all possible. Well, I guess it could be the XZ plane if we allow rho to be negative. If rho can be negative, because then that allows you to go back. But if rho is restricted to be non-negative, then it's just that back half. And I've kind of seen this both. If you want to do graphing, most of the time people allow rho to be a negative number. But if rho is only allowed to extend in the direction of theta and phi, then this would be, what do we call it? The back half of the XZ plane, i.e. XZ plane, but the X coordinate is less than or equal to 0. Does that make sense? Let me know if that does or not. Oops, sorry, okay. How about this one? Now I've got my pi over 6. Got my bearings. What's this look like? What is it shape? What do you think, Daniel?
Just a plane at height, pi 6, what is the axis?
It is not. It is not a plane. Yeah, Kayla, what do you think?
I don't know if this is right, but isn't it like a kind of cone
It's
shape?
a cone, yeah. Because it's saying, remember what phi was? Phi is how far you fall from the vertical axis, and then everything else can vary. So theta can vary. That line I drew could point in any direction, and rho can vary some along any point of it. So it's actually, yeah, it's a cone. It's a cone like that. This extends, of course, infinitely. I'll just kind of put that there to show it's infinitely. And then this angle, this interior angle is 30 degrees. So good to remember. So just like what I want you to do is have in your mind kind of the fundamental geodesics of this, the fundamental building blocks. In the same way that if we know, the fundamental blocks here are planes and lines, here the fundamental blocks are planes, cones, and then what is this?
Sphere.
That is a sphere of radius 2. So spheres, cones, and planes we have in spherical coordinates. So this is, and it's probably easier to draw a sphere first. At least I've learned that is the case. Make a little phony equator, stick some whiskers out of it, and there you go. And then, as much detail as you want. Draw your sphere first. That's if you leave this class with nothing else, that's good advice. Okay, so we've got that, and really quick, let's just do the same thing for cylindrical. So we have the same kind of visual dictionary. So in cylindrical, what is the following? So let's do z equals 2. You're gonna like that one, Daniel. That one. Theta equals 5 pi over 6, and r equals, let's do r equals 2. What are those fundamentals? Need any more tea, Eric? Are you still good? I'm still good. Okay. It didn't taste weird. Did it taste like, that's pretty good. Okay, cool. Yeah, this tea's pretty. Tell Sarah. Some fine drawings. Just run to the restroom, give you some time. First I'll come see what Cormier did, because he's our, oh, you thinking still?
Yeah.
Okay, good, I can go pee. I'd rather go do that. This is for, pain purposes and so forth. Being present. I gotta stop drinking tea all freaking day, I think. Might have a problem. Add more tea to your cup.
Oh, appreciate it.
You bet. Live to serve. Daniel, what's this one?
It's a plane at z equals 2.
Perfect, yeah. So this one, we have the z coordinate set at 2. And from this height, we can look in any direction, theta, and we can move out as far as we want. So it is a plane that goes right through z equals 2. And that's okay drawing, it's not a great drawing, but does this sound right to everybody? Sound okay? All right. What's the, hey Camila, what's this one?
That one was the one I didn't get. I think like you have to whip around like in a circle.
Okay, so yeah, okay, so,
Pi over 6.
so I'm gonna sweep, how many degrees is 5 pi over 6? This is an evil question in a way. How many degrees is this, or, that's 180 there, right?
Oh, yeah, yeah.
That's 180,
Yeah,
and so that's pi, and I back off a 6, pi over 6.
Okay.
So pi over 6 is how many degrees?
30?
30, perfect. So I want a 180, back up 30, 150.
Okay, yeah.
I'm just trying to like talk it through for everybody, not just you. So, yes ma'am. So I moved to 150 degrees. Radians. And then what does it look like from there?
Is it like upwards a cone?
I can move up any way I want, and I can move out. So it's again that plane that kind of shoots out that way. Does that make sense? Yeah, we don't get the cone yet. The cones come from, the cones are only in spherical. That's a good thing to keep in mind. So this is a plane that goes through here. Kind of sits at an angle. This would be pi over 6 right here. It's like, this is the same plane as theta equals negative pi over 6. Any questions on that? Yeah, yes, sir.
So R can be negative, but Z isn't in this case?
Oh, no, z could be negative here. In cylindrical, z could be negative.
Okay.
Yes, you're right. Yeah, it's just in the spherical. Sometimes rho can be negative, but sometimes it's restricted to non-negative. Is that sound
Yeah,
good?
yeah.
Okay, cool. What do we got here? What's the shape? 2.
What's up? It's
Sorry.
like a tube. It's like
A tube. Okay, I think you're saying tube. It looks like a tube. Tube. It's like a tube. Yeah, like a cylinder.
Yeah.
Right? Yeah, exactly. So here we've got a cylinder, and what's that radius, my friend?
2.
Exactly. So 2 and 2, and then we just got a cylinder that extends infinitely in both directions. Cool. Thanks. So in cylindrical, we've got, not shockingly, cylinders, planes, and a different kind of plane. But the key thing here is these cylinders are the hallmark of cylindrical coordinates, and that makes sense. So now, I'm going to give you some integrals, and we're going to convert them. And your first job is to figure out what is the region we're integrating over. So I'm going to give you a rectangular integral, and it's going to run like this: -2 to 2, integral negative root 4 minus x squared to positive 4 minus x squared, and then integral x squared plus y squared to 4 x dz dy dx. Convert it to cylindrical coordinates. So step 1, what the heck are we integrating over? What is that R?
We're going from rectangular to.
Rectangular, cylindrical first.
Cylindrical?
Cylindrical, yes sir. there's a lot of, sorry, question? No, it's just the noise. Remember your variable changes and all that kind of good stuff. But step one is, what the heck are we integrating over? You got some, or are you still pondering? You're pondering, okay,
I'm
cool.
pondering.
You're pondering, it's on the parallel processing. Yes, sir.
A question about the form.
Absolutely.
So when I look at this, I want to form like this.
Mm-hmm.
When I have my R here, does R still come out?
I would put the R in front, yeah, exactly, yeah, perfect. Agreed.
Yeah,
Yeah, yeah, and I think that's good, I think you got a good start here too. This stuff's pretty challenging, so I'm gonna spend the rest of the hour just working it. Awesome puzzles. That's good stuff, isn't it? Yeah. Comes in these little bricks, looks like a chocolate bar. It's really interesting, yeah. Break off little chunks.
Does it?
Yeah.
How much per ounce?
It does, it looks a little like ditchweed.
Yeah, I know.
Yeah.
I think I saw a little baggie.
I got a lot of little baggies in my office, but none of them are illegal. There's only a few things you have to do to remain a professor.
Okay.
Or do not do. Things to not do to stay a professor, and that's one of them. Put a bag of weed in my desk. Or at least don't let anybody know about it. It's good, that's on camera. They can bring the dogs in, I'm fine, I'm clean. Pat me down. It's like a, yeah, I'm gonna start working on this, and then we can kind of do sanity check, and then we can do the conversion of the integral. But let's make sure we understand what R does first. So the Z, this inner one, don't worry about that X. That integrand, we're just gonna use the formula X equals R cosine of theta, and we're gonna replace that X with this. So that's no big deal. But the other stuff, that's where the challenge comes. So let's just look at this integral right here, this innermost integral. This says Z runs from x squared plus y squared at the base, and then at the top there's z equals 4. And what does z equals 4 look like? Just a plane. This is a horizontal plane, right? Just cutting right through z equals 4. So we come over here. We're definitely going to have just a plane here at height 4. Let's try to make this picture look pretty decent as we go along. And then this bottom one. What the heck is the bottom one?
Is it a circle?
Paraboloid. It's circular when we look down from the top, but I think I saw Kayla mouthing paraboloid. Paraboloid. How do we know that? Well, look at the traces. When y equals 0, what does it look like? Parabola. When x equals 0, parabola. So I know that in the xz plane and in the yz plane, I see a parabola. So, oh, I wish I hadn't put this guy first. I'm gonna get rid of him. but I basically have something that kind of looks like that, like kind of the nose of a rocket, and then it's cut off, so this is z equals x squared plus y squared, and that is cut off at the top by the plane z equals 4. So you can think of the top as flat, and it's just cut by that plane. So let me stop there. Alexander, do you want me to explain that? Are you filled with joy? Look joyful. Anybody want me to talk? I'm happy to talk through this. Just let me know. All right. Nobody's seen Camille? Okay. Sorry. Sure. Yes, sir.
What's z equal for represent here?
So so think about what we're doing. We're going to rectangular coordinates, right? So I've got theta, the distance outward is r, and then the height is z. So z here is the same as the z here. That's good news. Yeah, does that sound okay?
Yeah.
All right. Is there a way to write this expression in polar coordinates? Yes, there is. What is it?
R squared.
That is r squared. So as we make our transition toward rectangular, we're going to note that this is r squared. So z goes from r squared to z equals 4. That's our inner integral. So let's actually start writing that. R squared to 4. And then x I'm going to replace with r cos theta. That's the substitution. I want to put my volume element here. So I have to remember that I have to incorporate an r. So I'm tossing in that r. And then this is going to be dz, dr, d theta. And we might change those. We'll see. But I definitely need the z, dz on the inside, because this is the z range. And I have to toss in that additional r for the volume element. Okay, so now we got this guy. Now we got to figure out, well, there's actually a few more restrictions here, so we haven't even like really kind of gotten these guys done yet. So this is saying, let's look at this outer integral. So we know this. What's happening here in these dx and dy is we're looking at what is the shadow we're integrating over down here. So it might not be everything under there. We've got to figure out what part of the xy plane is expressed by these outer two integrals. So notice the outer two integrals are just x and y stuff. So let's take a look. Let's look at the inner integral. So I've got this guy. And you're going to start seeing the same kinds of patterns over and over again. That's why we just need to work these things. I'm going to have dy. So that says y runs from negative square root 4 minus x squared to y equals positive square root 4 minus x squared. What is that shape?
Circle.
That's a circle. And I hope you've seen that enough times. These circles come up all the time. When you see a square root with an r squared minus whatever squared, that's a circle. So this is the positive y version. This is this half. What is the radius of the circle? 2. Beautiful. Cool. Minus 2. So that's the top, and then that's the bottom of the circle, right there. So this is this guy. This is the top half. Cool. So it looks like the y runs over a full circle, supposedly, but now what does the x do? So the x runs from minus 2 to 2. So look at how this goes. The x slices, these are our outermost slices, they're going to look like this. This describes the range of the vertical slices on the x. This describes how long, or the start and end of each of those slices. And then this tells us above each of those slices, how high did we go? Is that making some sense? Yeah? So what we've got here is a circle of radius 2. This just describes a circle, a full circle of radius 2. And so I come over here and I realize that this outer integral here has to express in RD, in R and theta, a circle of radius 2. So what does my R range have to be here? So let's 0 to 2, because we're gonna let theta sweep all the way around, and theta will point us in every direction if we let theta go from 0 to 2 pi. So my R runs from 0 to 2, and then theta runs from 0 to 2 pi. If it was only half a circle, or a portion of a circle, I could control that by changing where theta swept over there. We're gonna do some more, so this is kind of like intro 1, but now we got it. Yes, sir.
Can you explain again why you needed your -2 to 2 to have a full circle and not just the?
Yeah, absolutely. So what if I had done, that's a great question, Corbin. What if I had a 0 there?
Oh, so
Then I would only be doing the right half of the circle. Does that make sense? Yeah. Cool. Or, left half of the circle. Got that. How would we do just the bottom half of the circle? What would we tweak here? What if I just wanted to describe this? How would I change this integral up here?
Well, would you change like the second bound, like the dy bound from
Yeah.
negative, so keep the bottom, but then have it go to 0?
Yep, go to 0, and then x could run from -2 to 2.
Yeah.
Get that? And then if I wanted just that little critter,
You could just go from 0 to 2 on the x.
there we go. So see how we can just tweak those to get these various quadrants and stuff. Yes, sir?
How would it work if you, like, for the x integral, if you decided to integrate over a larger area?
Can you mean,
Like instead of going from -2 to 2, you go like to -3 to 3. Like, how does that?
well, so that would actually cause some problems. I think that's a great question. So if I put a -3 here, at some point x would equal -3. This would be an imaginary quantity.
Oh, okay.
We don't do that in this class.
Okay.
That's MT 480, which I hope you take one day, if it's ever offered in I don't know. It's complex analysis. It's complex calculus. It's awesome. Great class. Great class. Highly recommend. Has anybody taken that with me? Because I think I taught it last. Oh, such a good class. Okay, so you feel good on that, Talon?
Yeah.
Kind of address that. All right, let's try another one. We're not going to actually crank the integrals out. We're just working with understanding coordinate systems and changes. And is there? Oh, here it is. It's the next one. Integral 0 to 2. Integral 0 to square root of 4 minus x squared. Integral 0 to square root, whoa, that's a half-assed integral. Integral from 0 to the square root of 16 minus x squared minus y squared. And then the integrand is square root of x squared plus y squared. And then I've got dz, dy, dx. Cheers, my friend.
Thank you.
Thank you. Make sure to watch the recording.
Are we also converting this to?
Yes, rectangle. Or sorry, cylindrical, yes.
Cylindrical.
Yeah. Yes, sir.
I just have a question.
Yeah.
I just want to be confused. Like, do you recommend just to start like one by one?
Yes, definitely. Yeah, start on the inside, understand that. Yeah, exactly.
Yeah, because it's a lot if you just look at it all at once. Like, there's a lot of things happening here. We're definitely getting some practice with circles of radius too. That's cool. We've seen a friend we've seen before. Oh yeah, if you got those skills checks, let me get those before I forget, please. Mr. Czar slipped out. As crafty Czar. Thank you. Classic Cormick paperclip, beautiful. Thank you so, oh, wow, oh my God. It's okay. All good, thank you. Thank you. Thank you. Hey, thanks. Dude, thank you. Thank you.
I think I forgot to bring my desk.
What's that?
I think I forgot to bring my desk.
Did you forget? Okay, can you bring it by
Yeah.
Wednesday?
Of course.
Sounds good.
Or tomorrow if you're in.
Oh, I won't be in tomorrow.
Okay,
But, thank you. You gotta leave that.
Yeah.
Okay, cool.
Okay.
Yes, sir.
Does it really matter which way the do data on?
It doesn't. No, you can, you can often switch them unless one depends upon the other, and
Okay.
then it would matter, but otherwise.
As long as you keep track of it. Okay.
Yes, exactly.
Thanks.
All right, take care. Oh, thank you. No, it's all good. Thanks. I think I probably could recognize your handwriting by now, but I appreciate it. Thank you. Sometimes it's really hard to picture what the stuff is on that inner one, but you can still make variable changes even if you don't fully understand it. Just realize that inner integral, you just need to get that into R theta z. It's looking good. Looking at that first quadrant portion of the circle. And I got that. So this is the outer part I'm actually looking at. I see that I want y to run from 0 to y equals square root of 4 minus x squared. And you just have to get used to recognizing circle forms and see that this is y squared equals 4 minus x squared, y squared plus x squared equals 4. And this is just the top half of that circle of radius 2. So I drew that over there. Erstwhile, the x coordinate is starting at 0 and running to 2. So that means it's this quadrant right here, that little quarter slice. Is that okay? Yeah? Okay. Feels very deep in thought. All right, so in the meantime, so I'm just gonna actually put those guys down. I just kind of want to show you there's lots of different ways to approach this. I definitely need R d something. And I'm probably gonna do dz because that inner one's dz. Why mess with perfection? Z is z between the two coordinate systems. So I'm just gonna leave that there. And then out here, I'm going to put, looks like I already started kind of writing some stuff. D theta, dr. You could have dr d theta. Theta is gonna run from where? What's theta range?
0 to pi over 2.
Beautiful. 0 to pi halves, exactly. And then r runs
0 to 2.
beautiful. 0 to 2. And this, like, it's hard to kind of know exactly what that is. Does anybody have a sense?
Square root 16 minus r squared.
Yes, definitely. Yes, definitely. So we could just do that pretty straightforward change, realizing that x squared plus y squared is r squared. What does the roof shape look like?
Is it a sphere?
It is a sphere. It's a part of a sphere. Yeah, and how do we know that? Because this is z equals square root 16 minus x squared minus y squared. Be on the lookout for spheres and circles, because they're kind of the low-hanging fruit of all this stuff. And so, what is the radius on the sphere?
4.
Yeah, beautiful. 4 squared. So that is a sphere of radius 4. And that sits above this thing. So the sphere, this is actually a portion of that sphere. Let's look and see if we can fully understand this. So we've got the top half of the sphere of radius 4. And then underneath that, I'm actually just integrating over an area that's smaller than the radius of the sphere, because this is a circle of radius 2 under here. So what I'm looking at under here, let's get some axes. So there's z, and then this will be a reference for my x, and this will be a reference for my y. We are looking at this positive portion under here, but it's not the whole sphere. It's just this little shadow right there. And we're looking at the area that forms under this sphere. So it's kind of something like this that we're looking at. And that's a rounded top right there. So it's not the whole sphere, it's just the portion of this sphere underneath here. And this is a very spherical top, like that. So to get this guy, what we're gonna have is, yeah, we already got it. We've basically described it, so we're good to go. I just got to do this part. What does this turn into?
R.
Nice old R. There we go. Yes, sir.
How does the, so whenever you did the z to the z squared at the top, how did you get the plus between the x squared and the y squared?
I shifted I just added, I did. You're good at this kind of catching me on stuff. I screwed up. That's probably the answer every time. At least it has been today, every question you've asked me. It shouldn't be. Good call. Any other questions on this? Got a couple more. Let's use our time wisely. Because we don't meet the next 2 Fridays, right? We don't meet this Friday because we're off. School's closed this Friday. Awesome. It's great. And then next Friday's Math on the Quad Day. And I will have an assignment for you. I think one of your skill checks will be, do this problem, come do it on the pavement, make it look pretty, call me over, you get credit on the skill check. Does that sound good? I think that'll be skill check number 23.
When is it?
Next, the last Friday of the semester. Yeah. I'll be out on the quad from 12 to 3, and you just have to come find me sometime in that period of time while I get way too much sun. So here's another one. Yes, sir.
Do you have like 2 hours there or is it?
I'm sorry, what was that?
Is it like 2 hours?
Yes, r times r.
R.
So r squared would be the simplified. Yeah, good question. All right, here's another one. This one's a little tricky. I'm gonna write it in kind of the pretty way first, and then I'm gonna show you what I mean by that. But over the entire 3-dimensional space, square root of x squared plus y squared plus z squared, e to the negative x squared plus y squared plus z squared, dx, dy, dz. Now before we even talk about how to rewrite that, what coordinate system should I use?
Spherical.
Spherical. You've got this guy right here. This is r, this is rho. So I've got these. If you just had that, whoa, sorry Daniel. If you just had this, then that's like cylindrical town. But now that I've got x squared plus y squared plus z squared in 2 locations, that's just rho squared under there. It makes life so good. So here, if I want to actually put limits on this, to get everything, x has to run from minus infinity to plus infinity, y has to do the same, and z has to do the same. This is the kind of integral you want to like show your friends and family. That's a cool looking integral. That's badass. That looks like we're doing something serious. but we know it's not much. It's chill for us. So convert to spherical coordinates. And then if you're feeling super randy, find the area or find the value. Can we do this integral? We can't do it like that, I'll tell you. That ain't gonna work. Anybody seen Mr. Daniel? Not Dan, that's Dan.
I did see him.
So people have seen him.
He was man back.
Wow.
Yeah, like, what is?
Damn. Interesting. No comment. Thanks for the info.
Yeah.
Boy, oh boy, skipping one of your last 4 Calc 3 classes. Man, oh man. Hard to believe, Daniel. Getting ready. What does the integrand turn into? This. What does this become? Just rho, yeah, that's just rho. We actually even have that formula. And then what's this guy?
Rho squared.
Beautiful, that's rho squared. So this is going to become rho e to the negative rho squared. Sound okay? And then, let's see what else we got. We have got, what will be my phi, my, not my phi, my rho range? What does the radius have to extend from to?
0 to infinity.
0 to infinity. Gotta make sure you get every distance away from 0. How about theta? What is theta? 0 to 2 pi. We've gotta make sure we face in every direction. And then what is my phi range?
Also 0 to 2 pi.
We don't wanna spin all the way around. So
0 to
0 to pi.
Oh.
You don't need the like back wrap because theta gets you in the direction that you wanna go, right? And then you can just sweep down from that, so 0 to pi, right there. Now I thought this integral might be doable, but it's starting to look, it looks a little atrocious. I don't know about that. I just want to rewrite it and see how I feel about that. 0 to pi, integral 0 to 2 pi, integral 0 to infinity, rho cubed, yep, rho cubed, e to the negative rho squared, sine of phi theta d phi. Let's just talk about this integral. We can do this, but it's been a long time since any of us have done this kind of integral. Any idea on how, let's just, yeah, what are you thinking, Daniel?
At first I would try to, it's called integrate by parts.
Integration by parts, yeah, absolutely, yeah. So let's just take a look at this integral. This is calc class. So let's just look at this. Let's just look at this because this sine of phi, this can actually come out of that integral. Oh, I think I lost something here. or sorry, d rho. Where did I have my d? Did I lose him? Yeah, this should be d rho. Yes, thank you. Sorry about that. So this sine of phi is independent of rho. It could just come out of the integral, and really we just have to deal with this and then evaluate the limits. So if we were going to do integration by parts, we could write it like this, and let me just show you something here and see how you feel about it. So the reason I did that is because I can integrate this, because this is set up to integrate, and that I can differentiate. So what I would do is let u be rho squared, dv be rho e to the negative rho squared, and then du is 2 rho, d rho, and v is negative 1/2 e to the negative rho squared. You could do this backwards and see, take the derivative of this and see you get that. So that means this is going to turn into negative 1/2 rho negative, let's see, so wait, my v, uv, negative, this is going to be uv, so I got it settled out. So it's going to be rho squared times negative 1/2 e to the negative rho squared, that's uv, minus integral v du. Hey, that's cool, the 2 and the 1/2s cancel, the negative makes that a plus, and then this becomes rho e to the negative rho squared. That's pretty nice. That's pretty nice. Because now I just got the same integral again, right? This is the same thing as my dv from before. So this, I don't need to do anything now, just substitution on that. So this is negative 1/2 rho squared e to the negative rho squared minus 1/2 e to the negative rho squared. Sweet. And now I just have to figure out what the hell evaluating that at minus infinity and plus infinity would be. But don't get too stressed. I can argue this pretty easily in a way that I think you'll buy. So this is negative 1 over, this is negative rho squared over e rho squared. Just moving that underneath and with the 2. And then this is 1 over e to the rho squared. I just put it like that so we can think about it. So let's think about what is the value at infinity, what is the value at negative infinity. So it can't just be 0, but it sure feels.
Well, you're evaluating from 0 to infinity.
Thank you. Oh, yes. Thank God. Okay, thanks. That's good. I was a little okay. Thank you. That would have sucked. So when I plug in infinity here, when I let rho equal infinity, can you kind of think that through and tell me what you get? What do you get? Small ass numbers. How small? What's infinitely small and positive?
0.
Or not negative, right? Yeah, 0. So when I let rho, the limit of this, this goes to 0 as rho goes to infinity, is kind of what I'm trying to say, which seems reasonable, especially this piece right here, right? That's blowing up. But this blows up so much faster than the top that it still goes to 0. And then I just have to plug in 0. So we're going to have, when I evaluate this at rho equals 0, this dies. This becomes negative what? When rho equals 0? Negative 1, yeah. So this equals negative 1. This is the bit I would subtract, right? You would do top limit minus evaluation at lower limit. So that just turns into 1. This integral is just 1. That's pretty cool. That worked out hella good. So let's come back and knock that shit out. So we got integral 0 to pi, integral 0 to twice pi. This shit, we still have the sine of phi, but this whole thing became 1. So I got 1 sine of phi d theta d phi. The d phi, probably, we might as well flip this so we can just knock the freaking phi thing out. So that's going to be integral 0 to pi, negative cosine of phi from 0 to 2 pi, d theta.
You flip your,
Oh, did I screw something up?
well, you wanna flip your bound, like your, bounds,
Thank you.
right?
Yes, sir.
Yeah, yeah.
Yes, yes.
So it
Yes,
should
I
be like
do.
0 to
Good
2
call.
pi on the outer one.
Yes. Thank you, friends. Got it. Good stuff. I'm glad you're all here to keep me safe, help me cross the street safely, so forth, and just to be companionship. So when I put in the cosine of 2 pi is 1.
You wanna have that 2 pi pi?
Thanks. Woo! Almost fucked that up. I was like, oh shit, that's gonna become 0. That can't be. Everything's better with you all around. Cosine of pi is what? What's cosine of pi? Boy, it's quiet here. Negative 1, yes. So it's gonna be negative 1. And then minus cosine of 0, or negative cosine of 0. Now, what's cosine of 0? Negative 1. Awesome. So that's going to be 2 d phi. So that's 2 integral 0 to 2 pi d theta, and that's just 2 pi. That's 4 pi. You did it. Final value is 4 pi. Kind of hard to believe we could even do it, but we did it. And you're all ready to go, I see. I owe you a minute. Yes, sir. What's this? Yeah, so I switched the order on these guys. Yeah. Christian, my friend, would you mind?
Oh, of course.
Thank you. Daniel.